Sound and structural vibration signals provide a rich source of information during manipulation. In this work, we focus on the domain of manipulating granular materials and combine audio signals with machine learning to learn powerful feedback mechanisms. For our experiments, we used a 7° of freedom Sawyer robot arm. We filled a plastic tub with granular materials and rested the tub on top of 2 USB scales. Since each of our experiments involved estimating masses, we used these scales for recording ground truth masses for our datasets. We designed and printed a plastic scoop end effector and adhered a contact microphone to the back of its basin to record the vibrations in the scoop during manipulation. We collected a dataset of audio recordings of the robot pouring and shaking varying amounts of granular materials and recorded the ground truth mass of material poured out of the scoop or shaken within the scoop, respectively. Our dataset has 2,750 recordings of both shaking and pouring from each of 5 different granular materials, representing different material properties and applications of robotic manipulation. In our framework, we first compute a spectrogram of each audio recording. For estimating masses from these spectrograms, we designed different deep learning architectures, including convolutional and recurrent architectures, to compare their performance for this task of regression from an audio spectrogram. Here we show a diagram of our convolutional neural architecture on the left. Our proposed sum-GRU architecture on the right sequentially streamed each time slice through a gated recurrent unit and summed up non-negative estimates of poured masses from each time slice to generate a final mass estimate. Our deep models consistently outperformed our baselines of linear regression and static analysis of robot joint torques, achieving a root mean square error of only 2.8 grams on estimating masses of pores from 0 to 76 grams. Based on the promise of these results, we tried using our sum-GRU model for a real-time pouring control task. We chose a desired mass for the pour, and as the robot poured, we streamed the audio of the pour to our model until it estimated that the pour had reached the desired mass. Given the success of this simple controller, in the future, we would like to investigate how robots can learn to integrate audio frequency vibrations into real-time feedback systems in many more manipulation tasks.